Have you ever really thought about how a machine can teach itself to do something? You know, how it can learn to see, or write, or even create art. How does it get smarter every single time you give it new data? Well, that's one of the biggest, most fascinating questions in tech today. And right now, we're going to build a learning machine from the ground up, piece by piece, to see exactly how it works.
Okay, so let's just dive right in. And for a minute, let's forget all the complex code and the jargon. If you really want to get this, we've got to start with the absolute most basic part, the fundamental building block of machine intelligence. And it's actually inspired by our very own brains.
So say hello to the artificial neuron. The easiest way to think about it is like a single digital brain cell. Now, on its own, one neuron is pretty simple, not much to it. But the real magic, the whole secret sauce, happens when you connect millions or even billions of them together. But before we get there, we need to understand how just one of them thinks.
It's really just a simple three-step process. First up, it receives inputs. It's basically just listening to signals from its neighbors. Second, and this is the crucial part, it weighs the importance of every single one of those inputs. See, some signals matter more than others, and these little dials called synaptic weights are the key to this whole thing. And finally, if all those weighted signals add up and cross a certain threshold, the neuron fires, sending its own signal down the line. It's like a tiny democratic decision happening thousands of times a second.
Okay, so like I said, we don't just use one neuron. We connect millions of them, creating this huge, intricate network of tiny decision makers. So let's give our brand new network a job to do. A simple one, recognizing handwritten numbers. We're going to show it an image and see what it comes up with on its very first try.
All right, so we showed an image of the number 9, and it guesses 4. A complete failure. But here's the crazy part. This mistake, this failure, is the single most important thing that could have happened. This is the exact moment the learning actually begins. The failure is the feedback. That failure creates something we call an error signal. It's just a precise measurement of how wrong the network was. In this kind of setup, which is called supervised learning, that error signal is basically the teacher. It's the critical piece of feedback that tells the network, nope, not quite, try that again, but maybe adjust things this way.
And the whole point here isn't for the network to just memorize the right answers for the few pictures it's seen. The real goal, as this quote from the source material puts it, is something called generalization. We want the network to learn the underlying patterns, the essence of what makes a 9 look like a 9, so that it can correctly identify a 9 it has never, ever seen before. That's the real test of intelligence.
So the network knows it was wrong. It got the feedback. But now what? I mean, with potentially millions of these little connections, how in the world does it know which ones to change? Which of those tiny synaptic weights was the problem? How does it find the right path to the correct answer?
To get our heads around this, let's use a really powerful analogy. Imagine the total error of the network, how wrong it could possibly be as a massive foggy landscape. You've got towering mountains that represent huge errors, and you've got these deep, deep valleys that represent very low errors. The network has one and only one goal. Get to the bottom of the absolute deepest valley it can find. That's the sweet spot, the point of minimum error. But remember, the landscape is foggy. It can't see the whole map. It can only feel the slope of the ground right underneath its feet. So what does it do? It follows one incredibly simple rule. Always take a small step in the direction that feels steepest going downhill. That's it. This process has a name. It's called gradient descent. By always moving downhill, it basically guarantees that with every single step, it's getting a little less wrong. It's getting closer to the right answer. Now, the engine that makes this all possible is a really clever algorithm called backpropagation. You can think of it like a manager who calculates that steepest downhill direction. Then, it works backward through the entire network, telling every single neuron exactly how much to tweak its own little connections to help the whole system take that one coordinated step downhill together.
Okay, let's zoom out a bit, because this one simple idea, a network collectively walking downhill to get rid of its errors, is the fundamental principle behind some of the most powerful AI systems we have today, especially when we're talking about computer vision.
And this really shows you just how fast things can move once you get the fundamentals right. In 2012, a network called AlexNet made this huge breakthrough in image recognition. And then, just 1 year later, another network called ZFNet came along and improved on it in a big way. So how did it do that? Well, by having a better understanding of this whole learning process.
See, the creators of ZFNet, they didn't just start from scratch. They made small, really smart tweaks. For example,
They made the initial filters, those are the parts that look for basic stuff like edges and curves, they made them smaller. This let the network see finer details right from the get-go. They also reduced the stride, which just means the filter moved more carefully across the image, catching more information. These weren't random guesses. They were targeted changes designed to help the network find its way down that error hill more efficiently.
And what was the result of those small, clever tweaks? A really big drop in the error rate, all the way down to just over 11% on a massive image dataset. It just goes to show, mastering these fundamentals of how networks learn lets us build better and better systems faster and faster.
So, okay, why does all this matter? Why should you care about this internal machinery, the neurons, the error signals, the whole gradient descent thing? Because it has huge, practical, real-world consequences.
Well, for one, understanding this process helps developers make training way faster, which saves a ton of time and energy. It helps them build models that are more robust. Models that don't just memorize, but actually generalize. That way, a self-driving car can recognize a stop sign in the pouring rain, not just on a perfect sunny day. And it gives them the insight they need to design brand new network architectures to tackle even bigger challenges, everything from discovering new medicines to composing music.
So from a single neuron making one tiny decision to a massive network learning from its mistakes, we've basically built a brain that learns. This fundamental process, this step-by-step improvement, is now at the very heart of everything from medical diagnostics to our creative tools. And that leaves us with one last big question to think about. What is the next great problem these learning machines are going to solve?